All right. Let's get the last session started. So I'm Mariana Bertoni from Arizona State University, and I'm going to be chairing session 6 on reliability. So take your chairs. Our first speaker this afternoon is going to be Chihua Qian from Huazhu. She's the head of product development and management. The floor is yours.
Good afternoon, everyone. I'm Sarah. Today, I'm going to share comparison of PV plant value for N-type models in various scenarios. There are two main points I want to share: comparison of yield and PV plant ROI. ROI means return on investment in various scenarios. First, let me introduce Huazhu. Huazhu was founded in July of 2020. We focused on heat rejection technology, and we have large-scale manufacturing of wafer cells and modules. The headquarters of Huazhu is located in Xuancheng, China. Huazhu has 4 bases: Xuancheng, Hefei, Wuxi, and Dali, and our sales center is located in Nanjing. We have 20 GW annual capacity. We will achieve 40 GW by the end of 2024. In this part, we choose 3 types of models: the 630-watt IGT model and the 610-watt TOPCon model, and compared with the 615-watt BC models. BC has the highest power, maximum efficiency. IGT has the lowest VOC, which means IGT allows more models in each strings. IGT has the lowest annual degradation and temperature coefficient of max. Also, it has the highest bifaciality. They have the same size. There are 5 main factors this impact the yield: low irradiance efficiency, temperature coefficient of max, incident angles modified, bifaciality, annual degradation rate. Our experimental method. First, test the parameter of each model in labor according to IEC standard. Second, simulate the impact of each performance factor on power output using PVsyst. Third, test the power output in 3 environments based on demonstration plant, PV plant. We are partnered with 2 third-party, CTC and CPVT, and has built 3 PV plants in northmost, central, and southmost in China, for TOPCon. Both sides of IGT and are microcrystalline than a thin film with large band gap can absorb more light and high relative efficiency and low irradiation. This is shortly sample one diode model in PVsyst program. Due to imitation in the PVsyst model's low irradiance data in PANFARD cannot flat match actual text data. We choose 3 areas to simulate based on PVsyst. The figures show the performance ratio loss for the 3 modules. We can see, like IGT has the least loss, followed by BC. TOPCon has the most loss. This data based on PV plant. Compared BC, in HICO, LGT has 0.14% gain. TOPCon has 0.11% declined. In Yingchuan, LGT has 0.1% gain. TOPCon has 0.08% declined. In Mohe, LGT has a 0.33% gain. TOPCon has a 0.05% decline. Next, let's talk about the temperature coefficient. The left graph is the lab test data in different temperature. The right graph is the test temperature coefficient of models. Each model has two samples. The average temperature coefficient of LGT is minus 0.245. TOPCon is minus 0.3. BC minus 0.27. According to the product data sheet, the value is LGT is 0.24, TOPCon is 0.29, BC is 0.26, different with the lab test data. We import this data into the PVSys to simulate. In HICO, the average annual temperature is 24.9 degrees. The efficiency loss for LGT is lowest. BC is middle and TOPCon is highest. In Yingchuan, the temperature is 15.3 degrees. The efficiency loss for LGT is lowest. BC is middle and TOPCon is highest. But in Mohe, temperature is only 5.6 degrees. The temperature coefficient results in positive gain because the temperature coefficient of LGT is the lowest. The gain of HGT is the length. This data based on PV plant compared to BC. In HICO, LGT has 0.37% gain. TOPCon has 0.56% decline. In Yingchuan, LGT has a 0.18% gain. TOPCon has a 0.54% decline. In Mohe, LGT has a 0.45% decline. TOPCon has a 0.0% gain. As for IM, these are lab test data. When in distant angles is more than 60, the IM of LGT is 0.032, 0.05, less than BC. When in certain angles more than 70, the IM of TOPCon is 0.02, 0.5 more than BC. The figures show the function of AOI and AM with the time before 9 a.m. and after 4 p.m. AOI and AM has an obvious difference among three models. Usually, the IM is related to the numbers of ribbons. More ribbons, small IM. LGT uses 24 ribbons with 0.22 millimeters diameter. TOPCon uses 16 ribbons with 0.28 millimeter diameter. So IM of LGT has the most losses. BC has no ribbons on the front side. It loses the reflective light from the rainbow surface at large in certain angles. So BC is not doing better. This data or simulation use the PVSys in HICO. Due to the IAM difference, the performance ratio loss for HGT is largest. TOPCon is middle, BC is smallest. Intran and Moher are the same as HICO. This data based on PV plant. Compared to BC in HICO, HGT has 0.82% declined. TOPCon has 0.13% declined. Intran and Moher showed the same trend as HICO. This slide shows the bifacial impact. These data are lab tests. Let's look at the data. The average bifaciality of HGT is 88.4%. TOPCon is 78.2%, and BC is 68.7%. Let's look at the simulation data based on PV system. We use bifaciality in data sheet. This HGT is 19%, TOPCon is 80%, BC is 70%. Different with the lab test. Compared to BC in HICO, the albedo is 0.2. The percent ratio gain for HGT is 2.15% more, 1.04% for TOPCon. In Intran, the albedo is 0.2. The gain for HGT is 4% more, 1% for TOPCon. In Moher, albedo is 0.3. The gain for HGT is 2.47% more, 1.2% for TOPCon. This data based on play plant compared to BC in HICO. The gain for HGT is 1.92% more, 1.08% for TOPCon. In Intran, the gain for HGT 1.3% more, 0.74% for TOPCon. In Moher, the gain for HGT is 3.72% more, 1.84% for TOPCon. Got more because it snowed in Moher recently. Let's look at the demonstration PV plant. HICO is tropical monsoon climate with high temperature. We can see the yield in this plant during 1st October to 21st October in 2024. Compared to BC, HGT has 3.02% gain. For TOPCon, it has 0.32% decline. Moher in the north of China with low temperature, very low. We can see the yield in this plant at the same time compared to BC. HGT has 1.96% gain, 0.9% for TOPCon. Intran is the temperature continental climate with middle temperature. We can see the yield in this plant at the same time compared to BC. HGT has 1.84% gain, 0.09% for TOPCon. Next, we will focus on ROI in PV plant. In this part, we choose two typical locations: Qinghai in China and Riyadh, Saudi Arabia. 3 N-type models, 2 mountain structure fixed and tracker, and 2 foundation pair, and all of the accessories use 50-100 volt system and 1100 kilowatt inverter. Result is a typical desert accessories with high temperature and dry climate. This table shows the system configuration. As before, AGT has lower walls and temperature coefficient, so AGT allows for 28 models per strings, 2 more than BC, and there are 206 for fewer AGT strings than BC in the 106 megawatt PV plant on the DC side. Although the TOPCon also has a lower VOC, its temperature coefficient is higher. It allows for 27 models per strings, 1 more than the BC. The figures show the both of the plant compared to BC. AGT cost 0.21 cents more per watt. 0.82 cents for TOPCon. Both AGT and TOPCon has no advantage here. Compared to BC, AGT generation 44 more hours in the first year, and TOPCon has only 9 fewer hours. The higher yield of AGT models is due to the better performance in temperature coefficient, low irradiance, and bifacial. BC both in the city is lowest, but AGT IRR is highest. Qinghai, China is a typical Gobi Desert scenario with low temperature. Due to the same reasons, AGT allows for 26 models per string, 2 more than BC. So AGT save 308 strings than BC in the 100 megawatt plant. This is both of the plant compared to BC. AGT can save RMB 0.27 cents per watt, RMB 0.2 cents for TOPCon. AGT has an advantage here. Compared to BC, AGT generated 10 more hours in first year, and TOPCon has 4 more hours. Due to the low ambient temperature in this range, the low temperature coefficient is a negative factor. However, more radiance in AGT causes greater IM losses, which is removed the benefit of low irradiance and bifaciality. Compared to TOPCon and BC, AGT only generates 3 to 10 more hours of electricity per year. This project has the lowest both and higher yield for AGT, resulting in higher IRR. Thank you for your time. We have no more time to share. If you are interested, we can discuss in next time. Thank you very much.
Thank you. Well, we're a little bit way over time, so let's move on to our next speaker, Dana Kern from the National Renewable Energy Lab.
Hi, I'm Donna Kern from NREL, and I'll talk about our work in understanding degradation of silicon heterojunction modules. This is our team at NREL who provided all the work that I'll show you today. This is our institution, and here's the bifacial field that I'll talk about. Also, we welcome all of you to please come visit us at NREL anytime you want. We have a reliability workshop coming in March, so please come, we welcome you. Today I'll talk about two different sections. This first section will be on degradation rates in the bifacial field, and for the second section I'll talk about microscopy to understand the passivation loss in silicon heterojunction modules. So this is a video of our bifacial field. We have 10 rows that are all independently monitored and grid tied. They're bifacial, mostly PERC modules with monofacial counterparts and some bifacial silicon heterojunction modules as well. So this is an overview of all of the technologies in this field. So most of them are bifacial PERC with some monofacial counterparts of those, and then I'll try to compare the degradation rates of those to these silicon heterojunction modules. And we also welcome more of your silicon heterojunction modules if you'd like to add them to our field. So the first factor we'll look at is the bifacial gains. So overall, PERC is having a lower bifacial gain than silicon heterojunction modules, and those are values averaged over about 5 years. This graph shows the monthly bifacial gains, each averaged over 3 years. So for example, February would be February of 2020, 2021, and 2022, averaged to kind of average over the yearly changes, but still get the seasonal changes. So we see greater bifacial gains in the winter months because of snow, and in the summertime we see a greater bifacial gain for silicon heterojunction because of the better temperature coefficient for that technology. So this is, again, a comparison of those same values, just split out over the different years. So again, you see a greater bifacial gain of silicon heterojunction compared to PERC, but both of them seem to be decreasing while the modules degrade over the years. These are the performance loss rates for the modules in this field. So averaging together all of the PERC technologies, we see about minus 0.94% per year loss. And for the silicon heterojunction, it's a little bit more at minus 1.46% per year loss. So this is probably just an older type of silicon technology, or silicon heterojunction technology, and maybe they're getting better with processing over time. Overall, we're seeing a lower degradation rate for the monofacial counterparts of the PERC modules. This is that same data represented in a graphical format using RD tools. So we have a rolling average of a 24-month period, and then we plot it here. So the main takeaway here is that we have a higher degradation rate kind of early in time when the modules are initially mounted, and then the degradation rate decreases. These are the degradation parameters split out from indoor flash tests. So we can take the modules down from the field, bring them in, and flash test them every so often. This confirms that the silicon heterojunction modules were degrading at a faster rate compared to the PERC, and the monofacial was degrading less than the bifacial counterparts. Most of the degradation was in ISC, probably from optical losses, and there was also VOC degradation that followed, but not very much fill factor degradation, suggesting that there's not a lot of resistive changes in the modules. So then we can perform more analysis on why the modules degraded. This is an example of a bifacial PERC module. So we'll collect the external quantum efficiency with the front side measurement shown in blue and the rear side measurement shown in red. So external quantum efficiency is like the efficiency of extracting charge split out over these different wavelengths. And then down here we can take a difference plot to show which wavelength regions were degrading more between the control and the aged module. In this case, we see a signature that we assign to kind of a front side surface passivation loss. So we have greater loss when measuring from the front side in the short wavelength region and a relative gain out here in the long wavelength region. We confirm that when we do the current voltage curve. So in the IV curves, we see a VOC loss that we attribute to this greater carrier recombination from surface passivation loss. We have some ISC losses here from optical effects too. This is that same module shown in images. So we have photoluminescence, electroluminescence at a low injection level, then electroluminescence at a high injection level, and dark lock-in thermography, which is just the thermal signal of the module, and then comparing the control to the fielded module. We find that the overall intensity of the luminescence images has decreased to about 55% of the control, and that's consistent with greater carrier recombination causing that voltage loss. When we zoom in, this is just a bottom corner of the aged module. You can see that there are some dark bands on the electroluminescence images, and we've seen that before because of these small interconnect wires that can kind of disconnect near the edges of the cell, and we have other data to suggest that this is the rear side wires that are disconnecting. So this is a comparison with the monofacial counterpart of that PERC module. Again, in the EQE difference plot, we see a typical signature of front-side surface passivation loss, and that's reflected in this decrease in VOC. We see less ISC loss for the monofacial modules compared to the bifacial modules, suggesting that this maybe had a more stable encapsulant. Over here, this is the same type of imaging for the monofacial module. I guess, again, we see a decrease of the overall luminescence intensity to about 75% of the control. That's consistent with the VOC loss that was observed. If we zoom into the bottom corner of the aged module, we see in the electroluminescence images there is not that dark band structure, and that's consistent with less fill factor loss in the monofacial modules and a more stable wire connection on the rear side of the monofacial cells. This is a comparison to the bifacial silicon heterojunction module, and overall we see a different loss pattern for the silicon heterojunction compared to what we were seeing for PERC. So looking at the EQE, we do see lower EQE response in the short wavelength region, and we think that's consistent with this having a UV blocking encapsulant. Down here in the EQE difference plot, we see a decrease in the short wavelength region, which is still similar to that front side surface passivation loss that we were observing for the PERC. But then we see this additional decrease in the long wavelength region, both measurements from the front and the rear side. We think that the decrease in long wavelength regions from the rear side is just due to the longer carrier lifetimes in the silicon heterojunction modules, so you still see the impact of the front side surface passivation loss when measuring from the rear. The decrease from the front side in the long wavelength regions is potentially consistent with the degradation of the UV blocking encapsulant, creating some byproducts in that range. So these are the images for the silicon heterojunction module. Again, we see the overall luminescence intensity counts are decreasing, and that's consistent with the voltage loss that we've observed. But this is a different pattern where the uniformity of the luminescence images has actually improved with aging. So maybe there's some kind of burn-in effect, and this is consistent also with the very low fill factor loss in these modules, where the fill factor loss was less than for the PERC modules. So that was a summary of some field data, and now we'll talk a little bit about a microscopy analysis to understand where passivation loss comes from in these silicon heterojunction modules. So this is a different set of silicon heterojunction modules. These ones were aged outdoors for 10 years, and they had about 0.67% per year performance loss. The loss was mostly dominated by the VOC, and there was some decrease in fill factor that was correlated with an increase in series resistance. We then received another set of modules of the same type in the same year that was aged for the same period of time, but they were aged outdoors in Florida where the temperature is higher and there's more humidity in the air. So this is a comparison between modules that were aged in Colorado versus modules that were aged in Florida, where again these ones had higher humidity and higher temperatures. Overall, there was greater luminescence intensity decrease for the modules aged in Florida, which was consistent with the greater voltage loss. But we also see an extra resistance pattern along the outside edges of this module, which we think is moisture ingress from the edges that caused degradation of the TCO. So to understand the degradation, we use the image contrast of our different imaging types to select different categories of loss, and then we could core those out of the module. There's one of the cells in the module shown there, and then these circles, once we extract them out, that's about a 25 millimeter diameter circle. We can use these for microscopy, so those are luminescence images of the cored pieces, so we have relatively low loss, low breakage when extracting these pieces from the module, and then we can go on to do microscopic methods. So since the cells are still electrically functional, after we extract them from the cell, we can do measurements like this. This is a capacitance type measurement called deep level transient spectroscopy by Steve Johnston. So he would further isolate smaller 1 millimeter areas for the capacitance measurements. And he identified a defect level here labeled as E4 that was present in both of the weathered types of modules but not present in the control. By varying the voltage of his filling pulse, he could change the voltage-induced depletion width and get deeper or closer to the surface of the cell to probe the defect density. And he found a greater trap density closer to the surface, and the trap density decreased as he went away from the surface. And then in this case, I'll note that the junction is on the front side of the cell, and this type of manufacturer had better stability for their modules when the junction was moved to the rear side of the cell. So here we looked at other features of the front surface of this cell. This is an AFM-based measurement called scanning spreading resistance, where C.S. Jang was measuring the conductivity of the TCO to see if the TCO degraded. He found on average no statistical difference of the conductivity of the TCO between weathered modules and control modules. So then we look deeper away from the TCO towards the interface layers. So this is the indium oxide, the amorphous silicon layer, and the crystalline silicon layer with STEM. And so that's just a picture of where all the layers are, but we can chemically probe those with XPS with depth profiling to understand the chemical composition. So if we integrate these XPS peaks, we can get these kind of gradients of the different materials going into the cell. And we see that there may be a growth of a silicon oxide layer with aging. This confirms also that there's possibly a growth of the silicon oxide layer at the TCO interface with aging using EELS, electron energy loss spectroscopy done by Andrew Norman. And so this is something that we're looking into further. Well, that graph didn't work. But so we also used SIMS to test for the hydrogen profiles in the samples, and on average we saw that there was a out diffusion of hydrogen in these modules. So kind of to summarize, we see that there seems to be oxidation at the TCO silicon interface for the weathered modules, and is possibly also related to hydrogen out diffusion from the weathered modules. And those could relate to the defect level near that interface that we were probing with DLTS. So this is a summary of our observations. So first we talked about the bifacial field and saw a higher performance loss rate for silicon heterojunction modules compared to PERC. But again, these could be an older technology, and we would be interested to study newer technologies. And we saw that the bifacial modules were degrading faster than the monofacial counterparts. Most of the loss was dominated by VOC. The silicon heterojunction module also had additional encapsulant degradation that we think was because of an unstable encapsulant with a UV blocker. For the microscopic studies, we studied a different silicon heterojunction module that was aged outdoors for 10 years, and it was dominated by VOC loss, which we believe was related to these factors of the defect level near the surface, possible silicon hydrogen out diffusion, and growth of a silicon oxide layer near the TCO interface. So thank you for listening, and we welcome you to come to NREL anytime. Thank you.
I think we have time for a couple of questions. Any questions from the audience?
Thank you for the nice talk. You showed that there is a SiO(X) or a SiO2 forming at the TCO silicon interface. But do you see series resistance increase or fill factor decrease? Do you?
There is a fill factor decrease and an increase in series resistance as well. So we're wondering if this same feature is causing the increase in series resistance and the voltage loss kind of at the same time. Yeah.
I think the boss here.
So I have one question regarding your bifaciality assessment is only for PERC. when you say bifacial and monofacial, it's only for PERC structures.
Right, yeah. So the silicon heterojunction modules did not have a monofacial counterpart,
Okay.
but the bifaciality was still calculated from simulation.
So you don't know if in the case of heterojunction, you follow the same trend.
Yeah, so for the case of silicon heterojunction, the factor is still calculated, but there's not a monofacial counterpart that's fabricated and fielded there.
Okay,
Yeah.
thank you.
Yeah.
Thank you for clarifying.
I kicked something.
Hi, very nice talk. So if I understood correctly, the encapsulant for the heterojunction module was UV blocking. Is that correct? Yeah. Okay, and now you, like, as you indicated, there'll be a silicon oxide that's formed at the interface, TCO. So I'm wondering then, if the UV is blocking, so then, the interface damage, like the passivation should be good. So is this oxide because of the water ingress and it's, leading to the oxygen diffusing at the interface?
So yeah, that's an interesting question, and they are two different systems that were analyzed there. So the one that had the UV blocking additive was not the same one that was being analyzed for microscopy, and the module that was analyzed by microscopy did not have a UV blocking encapsulant. So that one had UV pass encapsulant for the one that grew the silicon oxide. So the one that's in the field with the UV blocking encapsulant, we have not cored it yet.
Okay,
Yeah.
thank you, thanks a lot.
Do we have any last minute questions? If not, let's thank Dana again. Our next speaker is Salvatore Lombardo from CNR IMM. So, the floor is yours.
Okay. Okay, good afternoon. My name is Salvo Lombardo. I work at National Research Council, Institute of Microelectronics and Microsystems, here in Catania. I would like to thank the organizers for inviting me to give this speech. So I will talk about bifacial photovoltaics modeling, data, and optimization. So first, I would like to acknowledge the co-authors of this work that are from CNR and from Trisam, and also the projects that have funded this research, which are national projects, IFOX and Best4U, and European projects, Ampere. So this is the outline of my talk. I will first talk about the bifacial PV concept, very briefly, you know very well. And then talk about model on bifacial PV and at the level of cells, modules, and strings. And then show some data and comparison model and data, and some few ideas, and go then to the summary. So the concept of bifacial photovoltaics, we all know, is the idea is to use the albedo light to increase the photocurrent, and the problem is to transform this into electrical power. The idea is quite old. It dates back to 1966. You see the reference to the original patent. And it stays around for quiescent for some time, but now is a very strong idea in the market. And the ITR PV roadmap reports that it will dominate the market in the next years. So let's describe very briefly the model. The model is essentially, clearly the first point is to calculate the photocurrent starting from the single cell. So the idea is to make a convolution of the quantum efficiency of the cell with the impinging light from the front. We have also to consider the photocurrent from the back, and this is again a convolution of the quantum efficiency on the back side with the light impinging from the back, and from the back is albedo light, and we have to consider all the ground, and each element of the ground sees under a certain solid angle the solar cell, and so it produces a certain amount of light collected by the cell. Then, by using the one-diode model, we calculate the IV curve of the cell. Then we put the cell in series, and we calculate the IV of the module. Then we put the module in series and calculate the IV curve of the string. Clearly, we need to have a model for temperature, and we use the most simple, but I think very useful model by Ross. It's a very old model. So the idea is that the cell temperature is the sum of the ambient temperature plus a term which depends on the intensity of the radiation. And there is a parameter which is the nominal operating condition temperature. This is true for the monofacial cell, but we assume it's also true for the bifacial cells. In the bifacial cells, we corrected the model by considering the light also impinging from the albedo, from the back of the cell. Okay, so let's see some results. This first example is a calculation, refers to a string of 5 modules. This is a calculation done close to the winter solstice at the latitude of Catania, 1 meter average height of the string, 35-degree inclination. Okay, here you see that clearly during the day, the light or the photocurrent, the short-circuit current of the string is far larger compared to the monofacial cell, and this difference is essentially due to the backside photocurrent collected from the backside of the cell. An important point to notice is that there is a large spread in the current collected by each cell. The change is very large. We go from 0.8 amps to 1.4 amps with an average current of 7 amps. So it's a huge change of about 8%. And clearly, what will happen is that we will read simply the lowest of these currents because all cells are in series. So this is a problem to consider. Okay, then let's see what happens in a string. In a string, the problem is even worse. And this is a calculation again. We are simply assuming that the cells are exactly all the same, but you can see that the fill factor of the string is very far from 100% or 80%, and this is simply because of the spread of the light collected from the backside of each module, actually of each cell. If we use a one-axis tracker, the situation improves, but still there is a change, a slope in the IV curve. Okay, let's see. The model is a 3D model. So it is useful because you can calculate the effect of the perimeter, which is extremely important because experiments are actually done on small strings. So it's useful to compare what's actually going on. And here is an example in which we change the size of the perimeter. We are considering, this is the case of spring equinox, 10 a.m. and latitude of Catania. Okay, and this is a calculation, I said. So this is a string of 30 modules, either, let's say, fixed orientation towards south, or with one-axis tracker, again, with the axis in the north-south direction. Okay, here you see the results, and again, you see that the photocurrent collected by the backside changes quite a lot, and you see there is more than 1 amp of difference depending on the position. So this is all energy which is lost, essentially. Nevertheless, there is clearly a minimum current that is still there. Okay, let's see the overall effect according to the model. This is here we're comparing the case of a string of 30 modules or 60 modules. Calculation is done at the latitude of Catania. Okay, here we're changing the perimeter size. This is without tracker, and this is with tracker, 30 modules and 60 modules. And the lines are 2D calculations that, are, as you can see, are quite different compared to the 3D calculations. And, okay, you see that clearly as the perimeter size increases, essentially, the energy yield increases quite a lot. It's a strong effect of many percentage points. Another point of the calculation is the effect of the power the temperature coefficient of the modules. In this calculation, we change the temperature coefficient in the range of silicon cells from the case of typical of a silicon heterojunction technology up to more standard, let's say, old-fashioned silicon cells. And you can see that this is the calculation for over 1 year. Clearly, you see that the bifacial gain is the largest for the lowest temperature coefficient, according to this model. Okay, so let's see some data. So our experimental setup is this. We use mini modules, not large modules, for safety reasons. And these are done by either 3 or 4 cells in series. And we measure clearly the irradiation conditions, the albedo, and the spectra, the direct, global, and diffuse spectra. Here is an example of data of short-circuit current, bifacial versus monofacial. And these are mini modules of 4 cells. And you see there is a large difference between monofacial and bifacial. The short-circuit current of the bifacial is roughly 20% larger than monofacial. And this is true for essentially all the orientation. Here we are changing the orientation in a wide range of angles. So is roughly 20% is true for essentially any angle. About the module temperature. The module temperature, to measure the temperature, we put thermocouples on the front and on the back of the cell. And essentially, in this particular example, I mean, it's a little bit difficult to distinguish the curves, but you see they're more or less quite similar in the case of bifacial, monofacial solar cells. There is not much of a difference. If we take the average of front side and back side, they're more or less similar. But if we do the experiment in another way, which is the following, we take our mini module and either we leave it bifacial or we cover the back side simply with a piece of paper, white paper. And in that case, what we're doing is simply shielding the backside. And so in that case, the difference between bifacial and monofacial modules is very large in terms of temperature. Bifacial is far warmer compared to monofacial. There is a roughly 15 degrees C difference in temperature. And we explain this simply as due by the fact that we have blocked the backside radiation. And so this reduces substantially the temperature. Okay, here is an example of a comparison between the model that we described before with some data. And okay, you see the model fits reasonably well the short-circuit current versus time. Okay, and as I said, there is about 15%, 20% difference between the short-circuit current between monofacial and bifacial. And if we go to the energy yield, then the difference is again roughly there, and is in this case, is about 15% difference between the energy yield of monofacial and bifacial. Okay. So as we described before, according to this description, there is a huge difference of illumination among the various cells that are all in series. And all this photocurrent essentially is lost. So one way to recover a little bit, or not a little bit, in some quantity, substantial quantity, this energy, electrical energy, is to use module level power electronics, so power optimizers essentially. And in this example, this is a calculation. We are considering a string of 5 modules. And we consider the case of a classical bypass diode. And this is the AV if we use the power optimizer. And then the power is this, the power versus voltage. And you see there is a substantial difference. So you gain about 6% energy, just like this. And if you have a shadowed cell that may occur, for example, in applications such as residential applications, in building integrated PV or so, you can have shadowed cells. And then the AV is strongly modified because of shadowed cells. And you see here that if we use this power optimizer, we would gain quite a lot, about 16.5% energy. Okay, then this was my last slide. So this brings me to the summary. I am run out of time, so you can read it by yourself. And thank you for your attention.
I think we have time for one quick question. Anybody? All right, everybody wants to go home, I think, or take the tour. So let's thank the speaker once again. Our next speaker is Felipe Valencia Arrojave, the CTO of Atamos Tech.
So thanks for the nice introduction. Yeah, I think it's okay. Thank you. So thanks for the nice introduction. I'm going to talk about the performance of heterojunction modules in high radiation and high humidity conditions. I'm going to start talking about what is Atamos Tech Corporation, and then I will move forward to show you our testing facilities, and then I will show you some of the results that we have found during the last 5 years of performance of heterojunction technologies there. So the Atamos Tech Corporation is basically a private-public consortium that involves national and international institutions with the aim of reducing as much as possible the levelized cost of energy in order to habilitate some other green sectors in Chile. For doing that, we have, among different things, 2 testing platforms. One is a 1 megawatt platform that we use for testing all the digital tools that we develop in order to digitalize the energy production in Chile. And also we use this platform to scale up the different other development that we have. Let's say tracking systems, some inverter technologies and these kind of things. and the Atacama Solar Platform, which is the main infrastructure that we use to test different module technologies so far. So the Atacama platform looks like this. There is a lot of sun, a lot of space, and a lot of nothing, just modules. Here we have two experiments running in parallel. The first one is the Atomo 1 cycle, which is running since 5 years ago, more or less. And the other one is the Atomo 2 cycle, which is running like 2.5 years ago. And this cycle was done with the cooperation of Trisan. In these structures, we have we have different module technologies, but at least we have 4 different heterojunction technologies. We have, of course, the technology from Trisan, but also we have some other, let's say, experimental heterojunction module technologies which are used to get information and improve the BOM in order to make more reliable the heterojunction modules in the future. So, in this solar platform, we have about 300 sensors. All of them are fully integrated in a homemade monitoring system that we use to operate remotely these platforms, because putting people there is quite difficult, and going there so often is also a very time-consuming and money-consuming and finally resource-consuming task. So we have different reference cells in the front, in the back. We have different cell monitoring temperatures. We have solar resource characterization station. The data of this characterization station is connected to the NASA system, so you can download the data from that page if you have access to it. So this platform is very fully instrumented, and we have a lot of information from there. So what we have, the first that I want to show you is what is happening since 5 years ago in the Atomo 1 cycle. Here you can see the front and the backward irradiance measured in each one of the structures. We have the vertical, the fixed, and the single axis tracking system. Given this information, you can see that in this case, depending on the structure, there are some technologies that perform better than other ones. But yeah, from the energy yield point of view, you can see that almost all of the testing technologies are pretty the same. But when you look at the performance ratio, the things changes a bit. Actually, the heterojunction technologies performs a little bit lower than the other ones. But this information was gathered, analyzed, and then some changes were made in order to have the new version of the modules and have technologies more adapted for the climate of the Atacama Desert. And this is what we are evaluating now in the Atomo 2 cycle. For the Atomo 2, we just have 2 infrastructures, vertical, single axis tracking and a fixed one. As you can see, the radiance is more or less the same that I showed before. The windrows is pretty the same. But what is changing is how the technology behaves. As you can see here, from the energy yield point of view, the behavior is pretty the same. But from the performance ratio point of view, now the heterojunction technology is performing better. But we did an experiment to see how sensitive is the heterojunction to the soiling, and we didn't clean up the plant since or about 6 months. And you can see how the performance ratio started to get down, until the performance ratio goes from the top to the bottom of all technologies. So in this sense, we saw that effectively something that we were looking at or we were realizing is that technologies with high bifacialities are very sensitive, at least in fixed structures, to the soiling and to the cleaning. So the question is how this started to grow. This is because here we have the winter season in the south of the world, and some self-cleaning phenomena started to take place. Then the plant started to clean up by itself, sorry. Something similar is happening with the single-axis tracking system. As you can see here, we have the Atamo 2 and the Atamo 2 Plus technologies. These technologies are also heterojunction and were made taking into consideration the information that was gathered from the Atamo 1 cycle. And as you can see here, all the heterojunction technologies outperforms the other ones. And the interesting thing is that when you have heterojunction in single-axis tracking structures, then you don't have problem or so much problem with the soiling. Here we have the same period with no cleaning, and as you can see, all the heterojunction technologies, independent of the tracking system, we have this one, and this one, are performing better than the other ones. So this is something that we started to think about because, we have to correlate test results with these numbers and then see how the tracking systems can be used in order to get more energy from the heterojunction technologies. In fact, as we see this increase in the fixed structure, we modified the tracking system control in order to promote the self-cleaning, because here we can put the tracking system in the position that we want in order to, instead having the flat during the night, we can put it in some angle and then take advantage of the humidity and the condensation to clean up all the plant. And as you can see, we were very lucky and we come with a nice result because self-cleaning get us back to the very top high performance ratio that we had. So as a summary, we did an evaluation during a year, every quarter, in order to see how much energy is getting from all the technology that we have in the Atamo 2 cycle. And as you can see, independent of the heterojunction technology that we have under evaluation, all of them outperform the other ones. Now we have just PERC technologies as a reference, and all of them are commercial products. And also, if we compare the different heterojunction among them, you can see that they behave pretty the same. There is just a slight difference between the amount of energy that they are producing. Complementary, we did a thermal evaluation of the behavior of the heterojunction technologies, since we characterized the albedo in the desert and we saw that there is a lot of inhomogeneous albedo in there. So what we were looking for is how the heterojunction technology deals with inhomogeneous albedo and how the inhomogeneous albedo is reflected into the performance of the technology. In this sense, you can see that at 10 a.m., for instance, you have the heterojunction 21, which is almost all the same temperature in all the modules. However, in the previous heterojunction version, there are some difference within the module and within the string. And the same happens with the PERC and PERC21, which indicates that we can have some additional degradation mechanism in the module because of these homogeneities. Since you have gradients within the module, and also you have gradients within the string, and then this can be translated to different amount of power provided by each one of the modules. If we go for the 11 hours, something similar happens. Here you have a very homogeneous temperature, but it's quite hot. Yeah. Here you have the heterojunction 21, which is the new version of the heterojunction technology, and you have a very nice homogeneous temperature pattern. This doesn't happen with the heterojunction 11 and the PERC 21. And for the single axis tracking system, something similar happens. But here is more difficult to conclude because the structure is moving, so the inhomogeneities are quite determined by the shadow of the tracking system into the soil, so this is quite different to see or to conclude something very hard. But something similar happens compared with the fixed structure. This is not at 10, this is at 11, sorry for that. Yeah. As a conclusion, you can see that from the energy production, we have a very nice technology to be used in the desert. And also from the thermal point of view, the performance is going well. So we are moving towards a technology that can be support high humidity and high radiation places. Finally, I want to invite you all to the BiFi 2025, which will take place in the Antofagasta. As part of this conference, you will have the opportunity to go to our facilities and see what is going on there. So you are very welcome for joining us in Antofagasta.
All right, any questions? I think we have time for one quick question. Go ahead.
Why you show the data of temperature with the tracker, and one row is much warmer than the other? But that's with the tracker, so I don't get that. Can you explain?
Yeah, because we don't use we use the morning hours because the albedo is more inhomogeneous. So as the tracking system is moving, the rows that are closer to the soil are hotter than the ones that are upper.
But that was like 20 degrees difference.
Yeah. And also, as the tracking system starts to get flat, the shadow starts to homogenize everything, and then they start to go down in temperature because you have a more homogeneous, let's say, albedo on the module.
All right, let's thank Felipe once again. So our last speaker of the workshop is Cha-Yun Yep. He's the product director of Ryzen Energy.
And thank you for the introduction. I'm Jia Jun from Ryzen Energy, and very pleasure to be here, and especially as a final speaker at the workshop. And I believe today is also another insightful and informative insights, and all are running in full capacity. So to ease a little bit, I will make my talk a little lighter. So my topic will be our challenges and difficulty overcoming in our mass productions. To begin, I will also a brief introduction of our companies. Ryzen Energy is also a PV module manufacturer, which was founded in 1986, but we started our cell and module manufacturing in 2002, which is 20 years history. And so far, we have accumulated the shipment over 91 gigawatt peak. And as just like Threeson, we started our heterojunction from 2018, and just 1 year later, we launched our first heterojunction product called Ziegler series. And we know that in 2022, the area was transferred to big wafer areas. That's why we designed our product with 210 wafer, launched our new heterojunction product called HyperIron. And just in next 2 years, we built 2 new facilities for only heterojunction production, which so far we have production base over 21 gigawatt production capacities. And with all the years R&D and experience in bringing heterojunction from lab to mass production, we have accumulated a lot of experience. And as we know that heterojunction technology was first introduced in the market by 1974, which is 50 years ago, not like TOPCon, which is 2013. But what takes this long to bring heterojunction to the market in commercial supply? The main reason we're thinking is that high cost for the for the productions, and among all the costs, the materialization part will be the has the highest share, I believe. And in the past years, silver consumption for the metallization for heterojunction is over 20 micrograms. We know that silver is quite expensive, right? And now by adopting which we have heard from the previous presentations, copper plating and low silver copper plated pasters, we can lower a lot the silver consumption. And in Ryzen, we are now have 2 paths, and we are now in mass production used the low silver paste, which means so far we have already reduced our silver consumption lower than 6 microgram per watt peak. And we are still working on it. And by end of this year, we're thinking it can be lower than 6 micrograms. So which by this, we already overcome the first barrier for the good commercial product for heterojunction. And what is next? Is I think the good commercial products will be consist of 3 good characters, which is lower cost and also higher reliability and higher efficiency. So what next we do is to maintain reliability when increasing efficiency. And what already are being mentioned many times in the yesterday, by Hwaseong and Longzhou, compared to TOPCon or TOPCon products, heterojunction more sensitive to high temperature. So we are trying to convert conventional production steps into low temperature ones. And the most important part we have observed is that we are not using the half-cutted cell technology anymore, because nowadays we are using the big wafer, and big wafer costs we have to use this half size to create interconnection. And the conventional way, we will produce the cell first, and using the laser and water blade to cut the cell in half. But the laser cutting is also with local high temperature, could have some thermal damaging on the passivation layer. That's why we change our conversion step, but produce the half-size ingot first, and have the half-size wafer produce a half-size cell directly on the half-size wafer, so we can avoid this loss caused by thermal damaging. And the same for conventional cell technology, we are using the welding technology, which is also of high temperature, it could be over 400 degrees. Thus, this is also not feasible to have to produce reliable heterojunction products. That's why we are now adopting our own patent hyperlink technology. It's kind of adhesive tape based interconnection technology, which means the interconnection between the cells will be just directly created by adhesive materials, but not welding technology. Thus, we can also avoid some like flux use in the model manufacturing, and we know the flux use sometimes cause some like residuals or some like delamination problem afterwards when the model was developed upon the product side. And also together with like hyperlink interconnection technology, we also adopt zero busbar technology, which can further reduce the silver consumption for the heterojunction productions. And by introducing the zero busbar technology, we know that we are not printing the busbar anymore directly on the surface, but replace a thinner ribbon with a thinner ribbon. And the ribbon we are using, which is much thinner compared to previous times. And the quantity we have is already improved from 16, 18 to 24. It's also optimal quantities for the ribbons on the surface. And by this way, we can reduce the shading from which cause like maybe power loss and hot spots. And also the thermal stressing on the surface will be more balanced compared to previous time, because we don't have like welding points or pad points from the surface to like attach the ribbons on the surface to make the fixations. So by introducing this, we are already reaching like quite a reliable products in terms of like microscope. But with nowadays with higher improved requirements for the applications, we are now have a lot more diverse. The application area was diversified a lot in recent years. Like we have also because of like climate change. Yeah, we have now hotter temperature, and sometimes in Europe we are also facing some hurricane, strong wind situation now, and also people are deploying a lot of floating PVs, requiring like model with higher water resistance. That's why based on this, we first introduced this thin wafer, which also been mentioned yesterday by by Huashang. And by the studies, we also shown that optimal efficiency for the heterojunction one will be reached between 80 to 100 micrograms. Not like conventional cell is like 130 or 150s. So the first step we do to improve the reliability is to reducing the cell thickness from 130 to 190 micrometer for so far. And by reducing cell thickness, we not only improve the efficiency, but also improve the bendability of the cell, which we can tell from this test. We have like different cells on the test devices, and the force will be given in the center, causing some deformations. And we found out that for like PORC ones or TOPCon one, by certain deformation, the cell will crack. But for heterojunction one, even when reaching the maximum of the test device, the cell structure will still remain intact after the force was drawn. And and even the cell can be rolled up. And but still the performance will not impact. We have done some tests for that. And also, this is also important for the nowadays case, because the model are become bigger and bigger. It is sometimes cannot be avoided if we have like central deformation in the cell or in the models. So with better bendability, we can better again resist this deformation in all the cases, like strong. Like a strong snow wind, like a snow load, and also wind load, and also to improve like resistance against like snow load and high wind load, we also introduced our own patented steel frame, which we redesigned aluminum frame with steel material, but stick to the same design. And by switching from aluminum to steel, we improve a lot the tear resistance in the mounting hole. We know that for some fixed structure insulation, people are using mounting hole insulation, the bolt insulation, and the mounting hole is the most fragile part in the model. And sometimes, if we're facing some like high strong wind, maybe this model will still remain intact, reliable, but the frame part in this mounting hole could taught apart. So with this steel frame, we can repel a lot the tear resistance under this case. And also the same, we also done some wind tunnel test to verify its performance under high-speed wind. And I think the video is not playing here, but it's showing that with the steel frame models, we done the highest level wind tunnel test. After test, still the model remained intact and the structure was not destructed. Yeah. And also, as you can see, the design of the steel frame are basically similar to the aluminum frame. and which means that it's very high compatibility to the conventional multi-structure design. Yeah, you can adopt this model still freely. Yeah. And also other topic was being raised many times in this workshop is UV conversion things, and this also matters a lot because nowadays, as I mentioned, we have new application scenarios in tropic regions with high UV radiation, like in Middle East and Africa, and we know that with high UV radiations, it could destruct the silicon hydrogen bond in the passivation layer, which would cause degradations. And in the past, we used to use UV cut films, which just blocks UV light, but not utilizes it. But for heterojunction technology, we know that the utilization in the UV light part, we are very low, not like TOPCon. Thus, we are by introducing the UV down conversion film, we can convert the UV light into the visible blue light, and utilize it part of the energy to improve, not only improve reliability, but also the efficiency. And by introducing this technology, I believe they are compared to a cutoff. You can see the transmittance will be the blue ones cut off filmed. And we can see out from here, the transmittance will be much lower compared to the cut-off films after years, which means we have better reliability. And with this film, we can also reduce a lot of UV degradation caused by the in this diagram, we can see after UV 60 test, the degradation loss we are 0.2% lower compared to the UV cut-off line film, and also the film we are using is kind of material maybe just last 15 years, 20 years, but after 15, 20 years, this UV down conversion film will work as a UV cut-off film, but not non-stopping film anymore. And by introducing, we also improve efficiency apart around 10 watt for our biggest models, 10 to 15s. And also the last improvement we make is to introducing upgrade our encapsulation for solution for some cases floating PVs, and to improve water resistant features. For example, we will seal all the openings to the environment. For example, we will have upgraded junction box and also the connectors. Especially need to mention is that we have some new metal sheet in the frame part to creating beside to seal the encapsulant or laminate from the outside door, which is we can see from here. This yellow part is a metal sheet here, and the red part is conventional glue we have. So we have 2-layer protection against moisture from the outside environment. Thus, with all the integrated new technology in the heterojunction products, we are now offering better, more reliable products for all the clients, and we have verified with different kind of tests like ammonia test, solid test, which is all here. And to summarize, we have to highlight some treatment that we have made. We are the first one in the industrial who mass produce zero bus technology for heterojunction, and also reduce solar cell thickness to 90 micrometers, and zero consumption lower than 6 micrograms, and also low temperature stress-free interconnection technology for heterojunctions. Yeah, that's why we launched just this month our new heterojunction products called Hyperion Pro. It's mass production in Q1 next year, and here are some key parameters for that. We see that it's a promising product in this year, and soon we will providing 740 Tom we mentioned yesterday by the end of the next year. And last, I would also show some ambitions of our company for the next steps. As now we are already reaching 740 watt in the next year. We are also trying to combine the BC structure with heterojunction. Try to launch some HVS products in 2026, 2 years later. And we also have R&D team established for study the combination of perovskite with heterojunction cell to launching some tandem cell products. We believe this will be first coming in 2027. Yeah, thank you.
All right, I think we have a question here.
The down conversion film that you were talking about, is it the same as mentioned by Jose Carlos Rozo, Rebo film?
Something also similar, but not same supplier. We have our own partners.
Oh.
Any other questions? I think we have a question there. She's going back.
Yeah, hi. A very nice talk. So you showed now that for the wafer thickness of 90 micron, you have means the wafer can have a very large, a very large deformation, correct? Compared to the 150 and 130 micron wafer thickness. Okay, so my question is, so in the cell production, you'll be having some vibrations. So what about the micro cracks and chipping for the reduced wafer thickness?
I will see, because according to our test, after this is not only a physical test, because after physical test, we also done some EL for check for both models. Okay. And according to our EL test, heterojunction 1 after the test, after this bending and recovering, is still within IEC standard.
Okay, so now when you compare say 90 micron and say 110 micron, so in the production, so the mechanical yield loss was not too higher for the reduced wafer thickness, if I understand?
I think so, yeah.
Okay, thank you.
Do we have any final questions? Well, if not, let's thank the speaker and let's thank everybody in this session and everybody in the workshop. Thank you.
Thank you, sir. So we have to finish the workshop and to give the appointment to the next one. It's edition number 8, and not decided the place yet. I think somewhere maybe in Asia. So I would like to thank all the participants and the speaker for the very high level of the presentation. I was very happy for this on many fields, from the technology, material science, equipment, reliability, so very high level of presentation. And so I would like to thank the organization, the University of Catania, the rector and Professor Terrasi, for giving us the opportunity of matching the beauty of the art with the science and technology in this beautiful place. And also Marina and my colleague from Trisan for the organization. And Sneh, if you want to say something for the organization.
Yeah, thank you, Cosmo. Thank you, everyone. I'm Chun Wang from SNEC. As some of you may know, SNEC as our event, SNEC PV Power Expo is the world's largest PV trade show with over 3,500 exhibitors from the PV and energy storage sectors this year. Taking this opportunity, I would like to extend our sincere gratitude to our partners, Trisan, the University of Catania, and also our sponsors, Tongwei, Huasan, Rise Technology, Borissil, as well as Exatech, and sorry, it's a little bit difficult for me. Old British Bridge, sorry. And for sure, I would also like to thank you to all the speakers and all the participants. And see you next year in China, hopefully. Okay. Thank you, everyone.
Thank you again. Bye to everybody.
So now, for who is visiting Trisan, you have to divide it in the 4 groups, the 4 colors. So let's start with the red group, please. Second is the blue group. So,